effect to determine what the maximum RPM is available in an engine. We can do a Mach index number calculation and determine that. And what that is determining the average speed of the gases as they rush past the valve into the cylinder. And when that average speed reaches about Mach 0.5, the peak speed is reaching about Mach 1, and trying to push it farther with a lower cylinder pressure is not going to get an increase in the mass flow rate during that time period. We're just going to stretch that time period out over a longer portion of the intake stroke. So we got here, here's some pumping loops from, these are from an actual engine. This one is down there. Up in the upper right-hand corner, at a variety of Mach index numbers, we have the result on the pumping loop. And you can see at a very low Mach index number, 0.2, the pumping loop begins to approach the idealized rectangular pumping loop, because the pressure drop across the valve becomes quite small relatively. Remember, it changes with the square of the velocity. Mach index number, I'll write it on the board in a second, is I've written on hand on here, with the definition of the terms that go into the Mach index number. Is that one or two? Okay. Basically, see if I can get one of these that writes. Mach index number is the bore squared times the mean piston speed times the diameter of the inlet valve squared. There's two inlet valves that include both the flow coefficient of the inlet valve and the speed of sound. Now those should be written and defined on the sheet that I gave you. The sheet, see. Yeah, we got Mach index number there, and I've got a definition of everything. There's a method of estimating the flow coefficient. It's somewhere in between 1.45 and 1.6 times the maximum lift divided by the diameter of the valve. But physically what we've got here is, if I multiply both sides times pi over 4, which eventually would cancel out, and here's, see, flow coefficient A, this is piston area, and this is mean piston speed. And this is inlet valve area, and this is the effective. By the time I've multiplied this times this is the flow coefficient, which is derived by taking the idealized flow. You calculate what would be the isentropic flow through this area and divide it into the measured flow, getting the flow coefficient. So this all together becomes the effective inlet valve area. And everything on the top here, this is idealized flow rate. All right. And of course, this is the speed of sound. So if I take the volumetric idealized flow rate and divide by the effective valve area, what do I get?
You get a flux, right?
You get the velocity, right? This is the velocity of the gases. Since this is the effective valve flow rate, this is the size of the valve, if it were isentropic, if it satisfied Bernoulli's equation, this would be the area. So I take the idealized flow and I divide it by the idealized area, I get the velocity, divide that by the speed of sound, and what do I got? I got the Mach number. And that Mach number increases with RPM. Mean piston speed is what? Stroke times RPM, and then divided by 2, takes 2 strokes, and whatever you have to do to fix the units. You want feet or inches or whatever. So this, for a given engine, given engine geometry, the Mach index number is a function of RPM only. So as we increase the Mach index number, all we're doing is increasing the RPM of a given engine. If we're going to compare 2 different engines, then of course they can have different Mach index numbers because the geometry of the engine can be different. Right? Now what was found, and you can see it in the plot in the lower left-hand side and the upper right-hand side. In the lower left-hand side, we have a given engine. Data is taken repetitively. And we can see that at Mach index about 0.5, the volumetric efficiency begins to drop. The vertical axis there is volumetric efficiency. The horizontal axis is Mach index number, which for a given engine is only a function of Z. Only a function of R.
Which figure is it?
The figure in the lower left-hand corner.
Yep.
We see a bunch of data, and we can see that as the Mach index number exceeds 0.5, the volumetric efficiency continues to drop. Which means at Mach index 0.5, we're going to begin to see a loss in horsepower because increasing the RPM, we're going to have a drop in torque, and eventually the percentage increase in RPM is not going to be sufficient to be larger than the drop in torque, and the horsepower begins to drop off. In the upper right-hand corner, we have a series of different engines running at anywhere from 25-20 feet per minute piston speed down to 367. Intake valve closing is always at 60 degrees after bottom dead center. For all the data in the upper right-hand side, it's 55 degrees after bottom dead center for everything in the lower left-hand side. And the fundamental way we can change the shape of this curve is when I close the intake valve. And we can see it's rather flat, the volumetric efficiency is rather flat until once again we hit about Mach index 0.5 or 0.6, and then it starts to drop. Yeah.
How does this graph go past Mach index 1 if you said you couldn't go faster than the speed of sound?
You can't, but you can. Mach index number is not a function.
It's just like a ratio, right? But how do
It's
you...
just a function of the RPM. We can, as long as the engine will make a higher RPM, we can go to a higher Mach index number. We may not get any more power out of it. We're certainly not going to get any higher mass flow rate.
But the efficiency
But yeah, the Mach index number is only a function of RPM, and this is the idealized flow.
Because you said that everything else goes constant at Mach index 1, why does the efficiency continue to go down then?
Well, this one is the true volumetric efficiency divided by the volumetric efficiency at 0.5. That's a ratio there. You see, the vertical axis in the upper right-hand side is the actual measured volumetric efficiency divided by the volumetric efficiency at Mach index 0.5. So 1 just means it's relatively constant over that range. The volumetric efficiency. It's not 100%, but it's relatively, whatever it is at Mach index 0.5, it's relatively stable.
Okay.
And we've changed here the ratios of exhaust to intake manifold pressure from 1.07 down to 0.05, wide range, and all this data falls in the same group. And you can see it's not completely constant, but it's close to. We changed the diameter of the intake valve from 1.05 down to 0.83. We changed the L to D ratio, the lift on the cam to the diameter of the intake valve from 0.25 down to 0.198. And we changed the flow coefficient from 0.365 down to 0.445.
I was looking at the wrong graph, my bad. I was looking at this one, not that one.
Okay. Things make more sense now?
Yeah, a little bit.
Great. So over a rather wide range, we still see when we hit Mach index 0.5 or maybe as high as 0.6. Of course, this is without a tuned intake or a tuned exhaust. These are very short passages, intake and exhaust, to collect this data. the volumetric efficiency starts to drop because a greater portion of the intake stroke is undergoing sonic throttling. At Mach index 0.5, we're probably just the peak flows have hit Mach 1. If it was constant Mach index 0.5, we wouldn't have any problem at all. If it was Mach 0.5, the whole intake stroke. But remember, the valve goes, its lift versus crank angle looks like that, and the flow coefficient looks like this. So if I do a cross plot, I'm going to end up with flow coefficient versus crank angle that looks like this. At the very top here, we hit Mach 1, but the average is more like Mach 0.5. So at Mach 0.5, we begin to experience a drop in volumetric efficiency because this portion of the intake stroke, even though we dropped the pressure lower in the cylinder with a higher RPM, cannot deliver more mass flow. We can't get more gases in the cylinder. And as we go to still higher RPM, this is a larger portion of the intake stroke, and we get to where we have a very small amount of fuel and air in the cylinder at a high RPM with a lot of friction, and we're not making any more power. So it's time to shift and go to a new gear, drop the RPM down, and go to the range again. Okay? Can you see the pumping loops on the right-hand side? We've got three cases here. We have, you're right, it's left-hand side. The, well, yeah, it's your left-hand side. The, we've got intake manifold pressure 7.4, that's half an atmosphere. What is the engine doing to develop an intake manifold pressure of 7.4 psi? What are we doing with the engine? If the intake manifold pressure is 7.4, what's the operating mode of the engine? If we drew a performance map.
That's a title.
Yeah, nearly. Particularly at Mach index 0.2, you're getting down next to idle. If we have a performance map, if we're at 0.7, we're somewhere here in the middle range. We've got about half an atmosphere pressure there. We now have, in all likelihood, sonic throttling at the intake plate where the throttle plate's closing. Now, if we want less flow, we got to close the throttle plate more and reduce the area because the velocity is going to be constant as a function of the atmospheric conditions. We have sonic throttling at the throttle itself. We have sonic throttling at the valve. That occurs after you get the throttle wide open. Okay. Now, for our intake manifold pressure 14.8 psi, what's that? Where was the gas pedal here at intake manifold pressure 7.4? We've taken our foot off the gas, right? For intake manifold pressure 14.8, what do we do on our foot? All the way down, wide open throttle. Wide open throttle. For intake manifold pressure 22.1, what's happening? Somebody added a supercharger or a turbocharger to the engine. We're still got our foot on the floor, but now we can go way above atmospheric pressure. As a matter of fact, depending on how big a supercharger or turbocharger we use, we can go much higher than this. This is only about 7 psi boost. Still enough to make a noticeable difference in how the car feels when we drive it. But nowhere near as high as we can go.
What is atmospheric pressure in psi?
14.7.
Okay, that's what I was
Varies day to day. Depends on how close you are to the hurricane. But it's generally accepted as 14.7 in psi. In inches of mercury is 29.92. So we've got three different operating conditions as far as manifold pressure, and we have Mach index 0.2, 0.4, 0.6, and 0.8. And what we see here, let's go to wide open throttle in the middle.
Was the first one 0.2?
The first one's 0.2. All the way at the top, you can look at the loop, see how the pumping loop nearly has corners on it. It comes down, here's the exhaust, and it comes down like this. Whoops. and it's nearly like our idealized one. That's because at a very low RPM, and Mach index 0.2 has to be a very low RPM, the pressure drop across the valve is becoming negligible. So we're approaching our idealized case. Now, as we go to higher and higher Mach index numbers, we have less and less time to get from here to here, and so we begin to have to go like this. Now, this is 14.7 PSI, or 14.8 we can call it. And as we get to Mach index 0.4, this still reaches atmospheric pressure again when we start the compression stroke, so we really haven't experienced a drop in volumetric efficiency yet. At Mach index 0.6, you'll see we have so little time, the gases are rushing into the cylinder, they never get back to atmospheric pressure and start to go up the compression. Here's compression, here's intake. Now we have less gases in the cylinder. We're beginning to see a drop in torque because we can't get enough fuel and air into the cylinder. And by Mach index 0.8, it's severe. You can see at Mach index 0.8, we got here, if this is atmospheric, we're coming down here and it's going like this. And whatever it is down here, when the intake valve closes, determines how much fuel and air we have in the cylinder to burn.
There's a lower pressure in this gas, right?
Yeah. The dotted line there.
Is atmospheric? No, that's.
Well, you see where it says 15 on the vertical axis. It says 0, 5, 10, 15.
Yes.
15 is approximately atmospheric pressure.
Yeah.
And in the case you see on the far right column, there's a dotted line at 22 psi. Yeah.
Will you explain one more time how come as you raise the Mach index number that
As you raise the Mach index number, we're getting less and less time to fill the cylinder. If we go from Mach index 0.2 to Mach index 0.4, we now have to fill the cylinder in half the time. To fill the cylinder in half the time, we're going to have to go to a lower pressure. And as we go up in Mach index number, we have to stay at this lower pressure for a longer length of time. Now at Mach index 0.4, we can still recover back to fundamentally atmospheric pressure, so we're not going to suffer a loss in volumetric efficiency. By Mach index 0.6, we don't quite make it back there. So we don't have as much fuel and air in the cylinder at Mach index 0.6 as we do at Mach index 0.4. And by the time we get to 0.8, we got a lot less.
The Mach index means the velocity of the intake gases, right?
Well, an
If you're flowing
idealized.
faster, why do we?
An idealized. Well, to get it to move faster, if the gases moved twice as fast, we have to have 4 times the pressure differential because it's turbulent flow. And the pressure drop needed to support the higher velocity is a function of the velocity squared. If you want to get the gases in the cylinder faster,
Yes.
you have to have a bigger pressure drop.
Yes.
And the pressure drop is the difference in between atmospheric, this is basically atmospheric exhaust, and the intake manifold pressure.
Yeah.
So as you go to higher Mach index number, you have to go to a lower intake manifold pressure because the atmosphere is just going to stay where it is.
For manifold injection, are Mach index numbers above 0.5 ever better for mixing?
Well, more turbulence is always better for mixing, for any delivery system. What happens as we transition laminar, we don't have any of those little eddies that can tend to rip up a water droplet or tear a water film off the intake manifold wall. So as you go faster and faster, the first thing that happens is you first transition from laminar to turbulent is you get relatively big eddies. And then as you go faster and faster, those big eddies break into smaller eddies. You still have the larger big eddy to a certain degree, but you have to dissipate more and more energy, and you need more and more eddies to do that. So as you get to, by the time you hit sonic, you've got extremely small scale eddies, and we'll see in future discussions that sonic throttling intake valves, which is what we're employing on the engine downstairs that reaches 38.8% thermal efficiency, have a wonderful produce a wonderful result in terms of burn rates. You can burn the mixture very, very fast. A very lean mixture, you can burn it very, very fast. And yet we don't have the bulk gas motion that causes the big heat losses in the combustion chamber. So BMW was the first company to do it. They developed sonic throttling intake valves. When you're driving a post-2001 BMW, when you're starting it, you can actually open and close the throttle. The rest of the time, the throttle's wide open and they're varying the lift.
Yeah.
So that what happens is if you want less power, the camshaft doesn't open the valve as much. And there's other mechanisms that allow you to affect the duration. Variable cam timing each manufacturer has come up with a way to do it. It's so beneficial, and you don't want to end up having to pay on patents from another company, so everybody develops their own.
Just to clarify, the picture you drew looks different from the picture. Is that that's at 0.2 Mach index?
Mach index 0.2 is very near the rectangular pumping loop that we draw when we assume instantaneous valve opening and no resistance to flow.
At full throttle.
When we did our PV diagrams, the reason we had this straight line here is we assumed we can open the intake valve instantaneously and there's no resistance to flow. When there's no resistance to flow, you immediately go to the lower pressure.
Right.
Well, at low RPM, the resistance to flow is very, very small, because that resistance to flow is a function of velocity squared. By the time you develop a passageway that's more than operational at wide open throttle at 6,000 RPM, when you're down at 1,000 RPM, it's 6 squared, 1/36 at least. Then you cut the gas velocity because you close the throttle. It's another, it certainly brings it to 1 to 100.
Right.
So you end up with a very, very small pressure drop needed. So this almost does this. It does this instead at Mach index 0.2. At Mach index 0.4, we only have half the time. So we have to go to a lower pressure to get the gases into the cylinder. And we almost return, well, Mach index 0.4, we were able to get back to atmospheric pressure. By Mach index 0.6, we're not quite reaching back, and we're beginning to experience a drop in volumetric efficiency. At Mach index 0.8, of course, it's a big drop. And you can see that best at wide open throttle from where the pumping loop turns around from the intake and starts the compression. What pressure is that occurring? And as you go to higher and higher Mach numbers, it occurs at a lower and lower pressure. In the case of Mach index 0.8, it's down close to 10 psi. 11, 10 psi. Whereas at Mach index 0.4, it's back up at 15 psi. We've filled the cylinder fundamentally with a near atmospheric pressure density. It's going to get a little hotter, so it's not going to quite be there.
Yeah.
It goes through hot passage.
But I'm still wondering, why is the exhaust valve opening at 20 psi in that picture?
Okay, we're not talking about the exhaust valve now, so
What's that top line? Because here the top line is
this is the exhaust stroke.
right.
Yeah.
And is that not on? But that's above 14.7.
Yeah, but the exhaust valve opens way over here somewhere.
Right. But
It's not in the draw. Yeah. Okay.
But why is it still above 14.7?
Because when you open the exhaust valve, you're way above atmospheric pressure. You get below down, you get down to atmospheric pressure, then the piston pushes the rest out at approximately atmospheric pressure.
But isn't that the top line? Because on
This is going this way,
yeah.
okay? We're pushing the gases out against the atmospheric pressure in the exhaust.
So it's still above atmospheric pressure?
But what's the hidden sense?
Well, because this picture is different from that picture. The picture.
Yeah, well, I'm not the best artist in the world, right?
Is that a wide open?
Let me, okay, which one do you want to talk about?
Are we talking about the top middle one?
The top
At
middle
wide
one,
open.
up here, all the way at the top.
Isn't that what
Yeah.
we've been talking about?
No.
No, we're talking about the bottom.
Close.
I thought we might be talking about
Bottom.
different things. Yeah. If you want to see the squares, is that what you want to talk about?
Well, I get. Okay, I just.
Okay.
I get it. I get it. If that's clear.
If the at wide open throttle the intake manifold pressure is the same as exhaust manifold pressure.
Right. That's.
So you're still gonna get a little pressure drop. Here comes the exhaust, the intake, get a little pressure drop because we can't get the intake valve open quick enough.
Yeah.
And then it follows along with atmospheric pressure and starts compression.
Okay.
That's Mach index 0.2.
Yes.
Okay, and then down from there, it gets steadily larger until eventually you come over here, and
So your picture, we were talking about part throttle? What was we even talking?
if you want to see the square, you gotta go to part throttle, yeah.
Okay.
Mach index 0.2 with manifold pressure 7.4. If we have the manifold pressure at wide open throttle and both manifolds the same pressure, we're not gonna see anything. Then our idealized one looks like this at wide open throttle. And these both take place at the same pressure. But if you want to see it look most similar to our idealized case, you have to assume that the pressure drop during the intake is negligible, and that occurs to the lowest Mach index number, which for this figure is Mach 0.2.
Right.
Perfect.
When the exhaust valve opens and we're coming back toward like that way in the graph, what do the waves represent?
Well, during the exhaust, there is always fluctuations in pressure. These are in the cylinder. The flow is never completely constant. It's not a stable flow at all. So it changes slightly, and consequently, we end up with pressure waves bouncing back and forth in the cylinder, and they show up on the PV diagram.
What's the reason for like as we go? It looks like as we're going down in Mach, or as we're increasing Mach number, like those waves start to.
And when the density is changing in the cylinder, density and temperature,
Okay.
and so the frequency changes. That wave is bouncing back at whatever the natural frequency is for that shape geometry, and it's changing too, and that temperature and that pressure, and that frequency is a function of those three things.
Out of curiosity, running like the Z of 0.18, if we wanted to go ahead and regain some of that pressure, let's say like, could we like blip I mean, obviously it doesn't, it's not something that exists now, but
Mach
could you-
index 0.8.
0.8.
Okay.
Yeah, so we're losing the volumetric efficiency. If I wanted to get that pressure up, like, would there be any benefit to like blipping the exhaust valve open really quick to bring the pressure up? If you were able to do it.
In which one?
The bottom, like the bottom left one, because you're.
Yeah, okay, parallel. Well, all you're gonna do is if you've got low pressure in the cylinder, you open the exhaust valve, well, at this point, we absolutely want the pressure low, because we're at low power output. Remember, we don't have our foot on the gas. If you're talking about the far left at the bottom, that's a situation where you got your foot off the gas because you don't want to run into the guy ahead of you. And so the one in the middle is back at wide open throttle. That's when we'd like pressure. But we don't want pressure from residuals. We want pressure from fuel and air because we want to make more power. And you know, you can do what they did here just to the right, and add a supercharger and turbocharger. You can put bigger valves in. You can put higher lift cam, more duration in the cam.
But what I'm saying is it possible to like pressurize the mixture with a little bit of exhaust gases to get the pressure? The
Not
initial
without
pressure up?
adding residuals. You can't raise the pressure without letting the gases into the cylinder.
No, I understand, but like how would that play? I mean, how would those residuals end up
Well,
affecting?
at wide open throttle, all you'll be doing is slowing the flame speed down.
So you're making
You're just adding mixture you can't burn. If you're at Mach index 0.8, you're adding mixture you can't burn. And then you're not gonna get any more power out of that. As a matter of fact, you end up with less. Okay? Now, the one thing we haven't mentioned yet in this whole discussion was to get us to the point where we could. If I have volumetric efficiency plotted against Mach index number, which for a given engine, remember, is a function of RPM only. We've got a curve that looks like this, right? And this is for intake valve closing 55 degrees after bottom dead center. That's the lower left-hand corner of the plot. Handed out. It says, in the lower left-hand corner it's after bottom 55, intake valve closes 55 degrees after bottom dead center.
Okay, well,
It's right in the middle.
Oh, I thought this one was.
why does the Mach index number go over 1?
This is 55 degrees after bottom dead center.
Stays constant. What is that? I don't know.
I must have Xeroxed the one that, I apologize. The Xerox, at the bottom, it's supposed to say 55 degrees after bottom dead center, as it does on mine, but not on the Xerox ones. So this would be 55 degrees after bottom dead center.
Not before.
That's when the intake valve closes. Or an intake stroke, there's no reason to close the intake valve bottom dead center. We still have a lot of momentum in the runners in the cylinder. We can take advantage of that momentum to get more gases into the cylinder if we leave the intake valve open.
Well, I guess my original question comes back here. So here you have the Mach index number going over 1, right? And you said everything stays constant once you go past the Mach index number of 1.
No. Once you hit the speed of sound, the mass flow rate, if you don't change the upstream pressure, stays constant.
Okay.
But you're trying to get it, your volumetric efficiency is a function of two things. How much space you're creating, which is a function of RPM, and what the actual flow rate is, right?
Okay.
The actual flow rate's constant, but as you go to a higher Mach index number, you're sweeping out more and more volume, so the volumetric efficiency goes down. Okay. So this is what happens at 55 degrees after top dead center. Over here, let's say 65 degrees after bottom dead center. The only way we can change the shape of the curve is to close the intake valve at a given time and make use of the momentum of the gases coming toward the intake valve when you hit bottom dead center. You still have momentum in those gases. If you leave the intake valve open, remember the piston's not going to rise rapidly after bottom dead center. We can continue to fill the cylinder. We want to close the intake valve at the instant the gases are not flowing in and they're going to get ready to start flowing out. Then we close the intake valve and forget them and stop them from flowing out. Now, what those trends look like, and I'm going to have to give you a couple of handouts because as many times as this has been discussed, they always make mistakes on the handouts. And so maybe you can spot them. I'll point them out to you so you don't end up being misinformed. But here are two plots. The original work was done by what is now NASA. And in the process of trying to reference it, there's always one mistake or the other. And so let me give you two different references for the original base of data. They are, unfortunately, there are two different mistakes in it.
Isn't this just a delight?
This is timeless.
Yeah, these two different.
Is there a difference?
Yeah. For a given engine, all of the other parameters, the bore, the stroke, and the diameter of the valve, are all constants. So when you see a plot versus Z, if it's only one engineer plotting, you're seeing a plot versus RPM. Okay. Now, what we can see here is as you close the intake valve, laser plate.
These are the exact same. These are the exact same, I'm saying.
No,
No, they're
two
not.
different mistakes on them.
On both of them?
And they're hardly exactly the same. As a matter of fact, if you want a good laugh, try and use this one.
Wait, we didn't get that. We got two of these.
We got
What's
these.
the difference?
Did
everybody?
No, I promise you. I promise you.
Okay, let me try again. Let me try again.
Yeah, no,
I mean, they're the same thing, they're just.
That's all you have.
You can try and use. Yeah, okay. Try and use this.
Okay, that's a different.
The other one you just use is scratch paper, you know?
So which one are we keeping?
That would be a test
I think
question.
this side got the right
What's
side.
the difference between these two?
We got the right side.
Oh my God.
People spend like.
You guys got the right one? You got the right one or the wrong one?
Wait, these are
You
the
got the
same?
right one.
Yeah.
All right, did you get the right one or the wrong one? You're not sure. Only this half of the room was.
Now we agree they are different. Okay, now we have three.
Now you got three. Well, two of them are identical. No, yeah, you just, make a paper airplane. Of the two that are not, can you see two of those three that are, well, I'm only talking to this side of the room. They got the right ones for some reason. Talk to the guy. Can you see the differences here? Okay. When they tried to define, in this one, when they tried to define the area that you're gonna use for the calculation of the flow coefficient, they defined it improperly. It's, this one's correct. You see? You make a plot. Let me do it on the board. Well, it's exactly what I just did here, but let me do it again without a bunch of other scribbles on the board. So that hopefully, no one will be distracted. Flow coefficient. This is lift. Lift versus crank angle. Now I make a plot of flow coefficient versus crank angle. And I end up with something that looks like this, because this looks like this. And as we go to higher lifts, this just exaggerates the shape of this. And then I go to, in this case, a lift that corresponds to 10% of this maximum. Here's the maximum lift. And I locate those 2 points, and I take this entire area, I take the average of that, and that's the flow coefficient that goes into the Mach index number. This average here equals our flow coefficient for the Mach index number.
I thought it's related to L over D, right? The flow coefficient?
No. L is lift,
Cranking.
and D is the diameter of the intake valve. You can, if you don't have this data, this is the data that comes off of a flow bench. We do flow bench analysis, we get this data. If you don't have this data, when you degree a cam, you get this data. You can begin to estimate what the flow coefficient could be by taking the lift, the maximum lift here.
Wait, is lift the distance that the valve gets open?
Right?
Is lift the distance the valve opens?
How do you define
This is the lift of the valve.
Okay.
How much, the most it's lifted, and you divide by the diameter for the head of the valve, And then you multiply, it's somewhere in the range of 1.4 times that to 1.6. If you do a really super good job, you can get up to 1.65.
It says 10% lift,
This is limit. We now do a cross plot. For each one of these lifts, we substitute in the flow coefficient. We have this, and then we can take the average value of that, and that's the flow coefficient for the port to go into the Mach index number.
What do you lift in this,
This is lifting the valve. The valve's on the seat here, and then as the crankshaft rotates, it goes to a maximum lift and back down again.
And you divide it by the diameter of the intake?
Yes, yes. And this is to just get an estimate of what it is if you don't experimentally have those two datas, which is the only way to do it.
I see.
Is it supposed to be symmetrical or asymmetrical?
Pardon me?
Is it symmetrical or asymmetrical?
Doesn't have to be. Doesn't have to be. Because of valve flow, you can open much more quickly than you can shut.
Is
So-
that what you're showing there?
Pardon me?
Is that what you're showing there? Or is that just?
Not particularly. No, all I'm trying to do is say, it's not square. If you open slowly at first because you want to take up the valve lash, you don't want to bang pieces together. You open slowly at first, then you go to your maximum lift rate, then you slow down again because you don't want the valve to be thrown off the tip of the cam, then come back down again and then slowly set it on the seat so it doesn't bounce.
So what was the mistake on this one? Like, what is the mistake?
In this one that has the correct area to integrate,
Yeah,
yeah, but try and use the data.
I've not used data. Not something there.
Take the curve for say 50 degrees after bottom dead center and follow it from one side of the graph to the other.
Oh. Yeah, it looks tough.
It's
What's that?
the
Oh,
wrong.
wow, it doesn't
It
matter.
gives you the wrong.
Yeah.
Oh.
This is
God, imagine if we had to.
Some graduate student somewhere said close enough.
The area.
Honestly, I can't even follow it.
That would give you. Okay, so
This one shows the proper area to integrate, and this one shows the proper behavior for volumetric efficiency versus a given intake valve closing.
wait, so what's wrong with this one? Not.
Let me see which one you got here. I handed out so many, I don't know what you got.
What's wrong here?
This area here, you want to take the average, but you want to take this area also underneath.
I see.
It's,
So
it's,
it
it's,
would
it's
be-
in
it would
between
be
these two
lower.
valve openings.
So it should be.
Yeah, and so, I don't know.
Okay, so is this,
Somebody does the graphic that doesn't know what it
is
is.
this the,
Yeah, you see,
okay.
see here, this is the proper area, in between this 10% lift to that 10% of max lift.
Oh, okay.
And this one completely negates all of that, so,
So this is correct or wrong?
this one's correct,
This is correct.
this is correct, that's incorrect.
What did you say this got the proper one? Before, just before.
Pardon me?
You said this got the proper area integrate?
Yeah,
Yeah.
yeah, the cross-hatched
Yeah.
area, you
So-
integrate and take the average
Okay,
of
so this
that.
shadow is correct. And you said this got proper one?
Yeah, this one's incorrect.
Yeah, but
They've forgotten all this area under here.
Just like this.
Yeah.
They're both correct.
Amazingly enough, if you look up other references, you'll find other mistakes. You know, it's apparently very difficult to duplicate the original data. And as I said, on this one, they say it's NASA data, but you can look through NASA till you're blue in the face. NASA used to be NACA. And so what you're looking for is, you see how I wrote it in there? I know you think I screwed up, but I didn't on this one. See, it's NACA text note 1366, the absolute Bible in Mach index numbers. And apparently there's a great variety.
That's right.